We move on to potential energy. As we learned in Physics 1, for the potential energy associated with position above the surface of the ground, if you have an object with mass m at height h, the potential energy is mgh. The potential energy depends on the position, right? So here we have another type of potential energy that we need to learn about, which we call it elastic potential energy. Elastic potential energy. So this energy also depends on position, depends on x, depends on the deformation. So here, when we push the spring, we compress the spring, eventually we are storing energy. This energy is a potential energy. Then when we press the trigger, this stored energy will be converted into kinetic energy that will make the ball moves and accelerate and leaves the nozzle with some kinetic energy. From the conservation of energy principle, we know that the kinetic energy of this bullet here is the same as the stored potential energy. It's the same energy, it is just changing the flavor from potential into kinetic. The potential energy can be calculated from this formula. It is half kx squared. K is the spring constant, and x is the compression, the displacement from the unstrained position. As we learned in Physics 1, mechanical energy for conservative forces is conserved. Elastic force is a conservative force. So the mechanical energy at any position, total mechanical energy at any position, the initial position, is equal to the total mechanical energy at the final position. We see here three terms to calculate the total mechanical energy: the kinetic energy, the potential energy due to gravity, and the potential energy due to elasticity. So these values in the initial position here are equal to the values in the final position here. However, sometimes there will be non-conservative forces like the force of friction. In that case, the difference between the final energy and the initial energy is equal to the work exerted against the non-conservative force, the force of friction. So these are useful formulas that we use when we solve problems. Let us learn a little bit more about this new form of energy, the elastic potential energy. Consider this situation that we started with. Again, you have this spring unstrained, unstretched, uncompressed, so x is 0. And you have this mass here on the surface, frictionless surface, there is no friction, moving with some initial velocity vi. Now this mass will hit the spring, will compress the spring, but before it does that, the total kinetic energy is half mv squared, half mv initial squared. As we learned in Physics 1, the kinetic energy is half mv squared. Now, when the mass starts compressing the spring, so now it is part of the original kinetic energy in the spring in the form of elastic potential energy. So at any moment, like this moment, the velocity now is v. The kinetic energy now is half mv squared. The potential energy is half kx squared. Remember that energy is conserved. So these two energies must be equal to the original energy, half mvi squared. Okay? Then the spring will restore its original position, move back, and there is a force exerted from the spring that will make the mass moves in the opposite direction. When the mass is not in contact with the spring, it is moving freely from the spring, then the velocity from the conservation of energy, we expect the velocity to be the same as the original velocity that we started with, because it's the same mass, it's the same kinetic energy. Okay? This is another situation of interest. When the spring is totally compressed, when it is totally compressed, there is maximum displacement from the unstrained position. The velocity here is zero. The velocity is zero. So there is no kinetic energy, which means now all of the energy is potential. All of the energy is elastic potential energy. Okay? Then in the third step, the spring now will start pushing on the mass. The mass starts accelerating back until we have this new situation. With the spring now may continue bouncing back and forth. Okay? And if there is no friction, it may continue doing that. Okay? Indefinitely. So this helps us to understand this interplay between kinetic energy and potential energy. This is another example. When the archer pulls back on the bowstring, the elastic potential energy is being stored here in both the bent bow and the stretched bowstring. Once she releases the arrow, the energy will be converted from elastic into kinetic. So now the arrow will start moving with kinetic energy with high velocity forward, right? And the energy is transferred from elastic to kinetic, just like we have here. Check your understanding. When an object moving in simple harmonic motion is at its maximum displacement from equilibrium, which of the following is at a maximum? Velocity, acceleration, or kinetic energy? Any suggestion?
I'm not sure, but I think it would be number 3, kinetic energy.
The right answer for this one is 2.
Oh,
because,
okay.
Yeah.
It makes sense, yeah.
So here, the acceleration is directly proportional to the displacement, and the displacement, we define it, the change in position, right? The value of x away from the equilibrium position. Thank you, Victor. We move on to learn about the velocity for a harmonic motion, like this motion, elastic motion, as a function of position. Based on what we learned so far, if you consider the oscillation of the mass with the spring, so here we attach the mass to the spring so it will oscillate back and forth with the spring. We started with some maximum amplitude A. We stretched the spring initially, and at this point the velocity is 0. We did not start motion yet. The velocity is 0. So the energy is all elastic. It is half Ka squared because x is equal to A. X here, x, the displacement, is the amplitude, A. So all the energy now is potential. The moment we let go, part of the energy now will be converted into kinetic, okay? As this mass moves, it will carry kinetic energy half mv squared. So the total energy that we have in the bank originally, which was elastic potential energy, now part of it is kinetic, the other part is elastic, okay? When x equals 0, this part is 0. So when x equals 0, the energy will be all kinetic, right? When x equals 0, from this formula, the energy will all be kinetic. This tells us something. The velocity is 0 before we release the mass, and when x equals 0 at this position, the velocity will be maximum, because now the energy is all kinetic. There is no potential. At this position, there is no potential energy. When x is 0, the potential energy is 0. So the energy is all kinetic. Therefore, the velocity at this point will be maximum. Okay? So the velocity changes from minimum value 0 to a maximum value, and the maximum value occurs when x equals 0. Then the mass will continue, the momentum will continue pushing on the spring, and it will start compressing the spring all the way until the spring is totally compressed. The displacement now is A. The energy now will all be potential because the mass will stop. When the mass stops, the velocity is 0 again, so kinetic energy is 0, and the energy is all potential energy. This situation is periodic. It can repeat over and over again with time, and if there is no friction, it will continue indefinitely. Okay, so we understand how the interplay between the kinetic energy and the potential energy for the oscillating spring. If we solve this equation for the velocity v, we get this result. V is plus or minus square root of k divided by m multiplied by a squared minus x squared. Okay, this is the equation for the velocity. K over m is a constant. You can take the square root of this constant outside. So v eventually is proportional to the square root of a squared minus x squared. Now ask yourself, what is a and what is x? A is the maximum displacement, the amplitude, and x is the instantaneous displacement from the unstrained position. Okay? So from this equation, we can predict the behavior of v. When x is equal to a squared minus a squared 0, the velocity is 0. We're talking about this end or the other end here. On the other hand, when x is 0, then square root of a squared is a, and we have the maximum value for the velocity here. Okay, it will be square root of k over m multiplied by a at this point.